Today's lesson is sourced from Chapter 3 of Mechanics of Materials. This video is part 1 of the lesson, in which we'll review the key concept. Stay tuned for part 2 in the next video, where we'll solve an example problem. We'll start by bridging the gap in our understanding of mechanical properties of materials. Be sure to review the previous videos on stress and strain, since we'll be building off of those concepts today. In this chapter, we'll combine what we know about stress and strain to see how they're related, and what they reveal about how a material behaves under loading. So we can examine a material's behavior by conducting what's called a tension or compression test. This test helps us determine the strength of a material, which is its ability to take on a load without significant deformations or failure. After experimentally testing the material, we can then graph all the normal stress values and their corresponding strain values. This graph is called a conventional stress-strain diagram, and it basically shows how stress varies with strain. We always put the strain values on the x-axis and the stress values on the y-axis. Stress-strain diagrams are actually really useful because they apply to a material of any size. So if you have 3 specimens of an aluminum alloy but of different sizes, they should still ideally produce the same stress-strain diagram. Again, that's because the diagram is specific to the specimen's composition, not its size. Okay, now let's take a look at an example of one of these diagrams. You can probably tell that there are 4 colored sections of the graph. You see a light orange and a dark orange, a light green and a dark green. These 4 regions all represent unique ways in how the material behaves. The light orange region is the elastic region. This is probably the most significant region for us to understand, because all our calculations are actually based on the assumption that the material is linear elastic. Now, if you don't know what linear elastic means quite yet, don't worry about it. We'll get to that in just a bit. But a unique aspect of the elastic region is that if the load is removed, the material will return back to its original shape without any damage. If you want to visualize this, think about what happens when you squeeze a stress ball and then let go. After you stop squeezing, it turns back into a sphere. Another thing you've probably noticed about the elastic region is that the graph is linear here. This means that stress and strain are directly proportional all the way up until the proportional limit, which is sigma sub PL. In other words, as stress increases, strain also increases by a numerical constant. This concept is known as Hooke's law and is represented by the equation sigma equals E times epsilon. The E is that numerical constant I just mentioned, and it's called the modulus of elasticity. The modulus of elasticity is the slope of the stress-strain curve in the elastic region, and it essentially indicates the stiffness of a material. Also, since strain is dimensionless, the modulus of elasticity has the same units as stress, such as psi, ksi, or pascals. Now let's talk about the dark orange region, which is called yielding. Anything from here on out will cause permanent deformation, which is also called plastic deformation. In this region, the material will continue to elongate without any increase in load. In other words, there is an increase in strain without any increase in stress. This is why the yielding region has a horizontal slope. When the slope is exactly 0, the material is said to be perfectly plastic. Next, we have strain hardening, which is represented by the light green region. When any additional load is applied, an increase in stress causes a non-proportional increase in strain. This happens all the way up until the ultimate stress, which is the maximum point of the stress-strain diagram. And lastly, we have necking, shown by the dark green region. Now that we're past the ultimate stress, Everything from here on out will cause the cross-sectional area to decrease in a localized region of the material. This basically means that a specific area of the specimen will constrict laterally and elongate longitudinally. By the way, CS area stands for cross-sectional area. So this will continue to happen all the way until the specimen breaks. And there we have it, the full explanation of a normal stress-strain diagram. For our next key concept, we'll be comparing ductile and brittle materials. Ductile materials can undergo large elongations before actually breaking. They're also better at undergoing tension than compression. An example of a ductile material is low-carbon steel. On the other hand, brittle materials show little to no yielding before failure. For example, gray cast iron usually experiences a microscopic crack somewhere, which then quickly spreads across the rest of the specimen and causes complete fracture. Brittle materials are better at undergoing compression than tension. This is why concrete usually needs some type of support when it's under tensile stress. For this purpose, engineers use reinforcing steel bars, also called rebar. Okay, remember when we touched on what it means to be linear elastic? We'll go into depth about that now. Judging from the phrase, you can probably guess that there are two main conditions for a material to be considered linear elastic. First, the stress must be linearly proportional to the strain and thereby satisfy Hooke's law. And second, the material must not permanently deform. In other words, when the applied load is removed, it must regain its original shape. Just two more key concepts to go. Now we'll review Poisson's ratio. Take a look at the image of the rubber block on the left. It's undergoing axial compression. After increasing the load, it'll look something like what you see in the image on the right. It contracts longitudinally and expands laterally. In other words, it undergoes negative strain in the vertical direction and positive strain in the horizontal direction. Within the elastic region, the ratio of these lateral and longitudinal strains is actually a constant called Poisson's ratio. It's mathematically represented by the Greek letter nu, and is the negative of the lateral strain over the longitudinal strain. Note that there is a negative sign. The negative is included because longitudinal elongation, or positive strain, causes lateral contraction, or negative strain, and vice versa. Since it's a strain over a strain, Poisson's ratio is dimensionless, and in future chapters you'll find that its maximum possible value is 0.5. And finally, we have our last key concept. We'll briefly skim over the shear stress-strain diagram since it's very similar to the normal stress-strain diagram. You can probably tell from its name that a shear stress-strain diagram shows how shear stress varies with shear strain for a material. Hooke's law for shear force follows the same format as Hooke's law for normal force, and is represented by tau equals G times gamma. G is called the modulus of rigidity. Just like E is the slope of the elastic range on a normal stress-strain diagram, G is the slope for a shear stress-strain diagram. We've now reviewed three different mechanical properties of materials: the modulus of elasticity, the modulus of rigidity, and Poisson's ratio. If you know 2 out of the 3 values, you can use the bottom equation to find the third value. Phew! I know that was a lot of info for one video, but I hope it helped you understand a little bit more about how stress and strain are related. Stay tuned for the next video, where we'll solve an example problem that incorporates several of the concepts we just learned. Thanks for watching!